Hello my dear students, welcome back to Fluid Mechanics lecture series. I am your Sumamis. My channel name is also Sumamis. You can watch my videos on my channel. Today we are continuing the discussion on non-uniform flow. So non-uniform flow classified into gradually varied flow and rapidly varied flow. In gradually varied flow, flow characteristics, that is flow depth velocity, changes gradually over a long distance. In rapidly varied flow, this flow characteristics, that is flow depth velocity, changes suddenly over a short stretch of the channel. So one of the example of rapidly varied flow is the hydraulic jumper. The phenomenon of sudden increase in the depth of the flow due to the transition of the flow from supercritical to subcritical is called hydraulic jumper. So it is also called a standing wave or stationary wave in a channel flow. The hydraulic jump is formed at a section where low depth stream of high velocity strikes sufficient depth of liquid flowing with low velocity. So the incoming flow is supercritical state, whereas it strikes the subcritical state of flow, and hydraulic jump forms at this meeting point. So when the hydraulic jump occurs in a flow, the depth of flow increases suddenly and the flow experiences a considerable energy loss due to eddy formation and turbulence. Since the depth of flow in a hydraulic jump suddenly changes, the phenomenon can be categorized as rapidly varied non-uniform flow. Since the non-uniformity is limited to a short distance, the hydraulic jump represents a local phenomenon. The hydraulic jump also forms when the liquid flows out from a spillway. So in this case, the idea of the creating jump is to dissipate the large amount of energy that is carried by this water. Otherwise, it will score the entire downstream structure. So another situation where the hydraulic jump occurs is the downstream of the sluice from which water comes out with a depth less than the critical depth. So this total line represents the critical depth line, and the flow depth of this incoming flow is less than the critical depth. That means the flow here is supercritical stage and it meets the subcritical flow at the downstream side, and hydraulic jump is formed at this location. So the apparent effect of hydraulic jump is the increasing water level. Now let us discuss about the energy loss associated with the formation of the hydraulic jump. Consider the formation of the hydraulic jump in a prismatic channel with a horizontal bed. When the hydraulic jump occurs in a channel, the flow depth increases suddenly and the flow experiences considerable energy loss with eddy formation and turbulence. Y1 and V1 are the flow depth and velocity just before the jump, and Y2 and V2 are the flow depth and velocity after the jump. If we are drawing a specific energy curve, the minimum point is corresponding to the critical depth Yc. Y1 is the flow depth before the jump and the corresponding specific energy is equal to E1, and Y2 is the flow depth after the hydraulic jump and the corresponding specific energy that is equal to E2. So you can see that E2 is less than E1, or delta E, that is equal to E1 minus E2. So because of this energy loss, the depth after the jump is less than the alternate depth corresponding to the specific energy at the section 1. So because of this unaccountable energy loss, one cannot use energy concept for the analysis of the rapidly varied flow. So we have learned previously that in a rapidly varied flow, we have to use specific force curve with the concept that specific force at the section 1 equal to at the specific force at the section 2, that is equal to F. So if we are drawing the vertical at F, it will cut the 2 points on the specific force curve corresponding to the flow depth Y1 and Y2. So these Y1 and Y2 are the flow depth before and after the jump. So these two depths are called sequent or conjugate depth. Now we can derive the expression for the sequent depth in a hydraulic jump in a horizontal rectangular channel. Consider a hydraulic jump forms in a prismatic channel of width B with the horizontal floor carrying a discharge Q. Based on the momentum concept, we can say the specific force at the section 1, that is F1, which is equal to the specific force at the section 2, that is F1 equal to F2. So what is specific force F1? F1 equal to Q square by GA1 plus A1 Z1 bar, and F2 that is equal to Q square by GA2 plus A2 Z2 bar. So here A1 that is equal to B into Y1 and A2 that is equal to B into Y2, and Z1 bar is the distance of the point of application of this pressure force with respect to the free surface, and Z2 bar is the distance from the free surface to the point of application of the pressure force P2. So Z1 bar equal to Y1 by 2 and Z2 bar which is equal to Y2 by 2. So if you are substituting for A1 and A2 and Z1 bar and Z2 bar, then we can modify this equation as Q square by G into By1 plus B into Y1 by 2 equal to Q square by G into By2 plus By2 into Y2 by 2. So if you are dividing LHS and RHS by B, then this equation becomes Q square by GB square into 1 by Y1 minus 1 by Y2 equal to half into, this equation becomes Y1 square minus Y2 square. So Y1 square minus Y2 square can be simplified into Y2 minus Y1 into Y2 plus Y1. Q by B can be written as small q. So if you are replacing Q square by B square as Q square, now this equation can be written as Q square by G into Y2 minus Y1 divided by Y2 Y1 equal to half into Y2 minus Y1 into Y2 plus Y1. So we can eliminate the common terms from LHS and RHS. This term and this term can be cancelled. Then we can simplify. So it can be written as 2Q square by G equal to Y2 Y1 into Y2 plus Y1. So Y1 and Y2 are the sequence depth and Q is the discharge per unit width. So this equation represents the momentum equation for a hydraulic jump in a rectangular channel. Now we can discuss about a different type of equations connecting Y2, Y1 and Q. So if you are expanding this equation, it becomes a quadratic equation, either can be expressed for Y2 or Y1. So if you are expanding this equation, Y2 can be written as minus Y1 by 2 plus root of Y1 by 2 the whole square plus 2Q square by GY1, or Y1 can be written as Y1 equal to minus Y2 by 2 plus root of Y2 by 2 the whole square plus 2Q square by GY2. That means if you know any of the sequence depth and discharge, then other depth can be determined. This equation can also modified as Y2 by Y1 equal to half into minus 1 plus root of 1 plus 8Q square by GY1 cube, and Y1 by Y2 equal to half into minus 1 plus root of 1 plus 8Q square by GY2 cube. But what is Q square by G? Q square by G equal to YC cube. So in this portion, Q square by G is replaced by YC cube. So this equation becomes Y2 by Y1 equal to half into minus 1 plus root of 1 plus 8 YC cube by Y1 cube. Similarly, we can write this expression also. This equation also can be represented in terms of root number. So root number at the section 1 equal to V1 by root of GY1. So V1 equal to Q by Y1, where Q is the discharge per unit width, or FR1 square can be written as Q square by GY1 cube, and FR2 square can be written as Q square by GY2 cube. So this term, that is Q square by GY1 cube, can be represented by means of FR1 square. Similarly, Q square by GY2 cube can be represented by means of root number square at the section 2. So this equation now can be written as Y2 by Y1 equal to half into minus 1 plus root of 1 plus 8 FR1 square, where FR1 is the root number before the jump. And this equation can be written as Y1 by Y2 equal to half into minus 1 plus root of 1 plus 8 FR2 square, where FR2 is the root number after the jump. So these are the different forms of the equations which we can connect this YC fluid number, and sequence depth and discharge. Now, today's session comes to an end. We had enough discussion about the rapidly varied flow and how momentum concept can be used to derive dynamic equation of hydraulic jump in a rectangular channel. We have also established different type of relationship connecting sequence depth and discharge. So for the time being, it is enough.